Hey, in this video, we are going to start talking about the central limit theorem and how it relates to the normal distribution that we talked about in the last chapter. So here we have 7.1, the central limit theorem. And this tells us that for a population with any distribution, so that means skewed left, skewed right, uniform, or Bell, that the mean of a sufficiently large sample will approximately follow a normal distribution. So if our sample size is big enough, then it doesn't really matter about what the distribution of the population looks like. The sample will be approximately normal, which lets us use all of the tools that we used or learned in chapter 6. There are two central limit theorems. The first one that we're going to talk about is the central limit theorem for means. And that says, again, if we have a large enough sample, we're sampling from a population with a finite variance, our distribution will be approximately normal. So again, by having that the distribution being approximately normal, we can use those tools that we learned in chapter 6. It tells us the sample mean will equal the population mean. So you can see that in the first box right here. Remember, the sample mean is the regular letters like X, and the population mean is the Greek letter mu. And then it says the sample variance will equal the population variance divided by n. Instead of writing out variance, I wrote it out as the standard deviation. So I just took the square root of both sides already. So we have S equals our sigma over the square root of n. That's why it says divided by n up here. But it's square root of n over here because I already took the square root of both sides. Okay, what does sufficiently large mean? Well, sufficiently large is actually probably going to seem quite small because it's really just 30. If n is greater than 30, then the sample means we'll have a distribution that's approximately normal already. It doesn't matter what the original distribution is. If n is less than or equal to 30 and the original population is normal, then we're good to go. The sample is already normal. If n is less than or equal to 30 and the original population is not normal, those two things will make it so we can't use the methods in this section. But really, if n is less than 30, what are we even doing? We need to have at least 30 things in our data set. Okay, so we're going to use the central limit theorem. I just usually abbreviate it CLT. We're going to do the central limit theorem for means, and we're going to find the mean and standard deviation using these formulas. And by mean and standard deviation, I mean for the central limit theorem of means. So that would be the sample mean and the sample standard deviation. Okay, so writing out in here. Now this is going to be a little tricky because I don't think I can write in Greek with this keyboard. Maybe I'll just try to write it with the pen. Okay, so the temperature is recorded at 60 airports. So that is our N, because that's the number of airports. The temperature, it says average right here. The average temperature is 67, so that's our mu. And the standard deviation is 5, so that's our sigma. And the question is asking what is, I don't like this, this is going to take too long. I'll probably switch in a minute, but at least we can see the first couple like this. What is X bar and what is S? So X bar is going to equal mu. So that is simply 67. And S is going to equal sigma divided by the square root of n. So we have 5, kind of looks like a 5 over here, that's S, over the square root of 60. Okay, I'm not doing this again, but you at least get the idea of what I'm talking about. X bar equals 67, S equals 5 over the square root of 60. Just leave it like that. You don't need to simplify. You don't need to get it in decimal form. When we get to the longer problems and we start typing it in the calculator, S, which is 5 over the square root of 60, that's exactly how we're going to write it in the calculator. Okay, let's go on to number 2. So number 2 says a class of 30 kids compares what they receive while trick-or-treating. They find that the average number, so average is mean, is 73, and the standard deviation is 3. So we know n is 30. because there's 30 kids in the class. So that's perfect. We have our 30. And then it says they receive the average number. So this is going to be our mu. And then a standard deviation of 3. I'm just going to write out these in words because I can't, I don't have the symbols on my calculator. On my keyboard. With standard deviation of 3, which is our sigma. So x bar equals 73 because x bar equals mu. S equals, and this is sigma over the square root of 30. So here I'm going to need to, I can't do square root. Let me get my line. So here's my fraction. And then how fancy is this going to let me draw a square root? Let's see. I missed square root of 30. And again, that's it. Leave it. We don't want to change to decimals because if we change to decimals, then we're going to round. And if we round, then we affect the final answer. So just leave it in radical notation. Leave it as fractions. Don't simplify anything. Okay, number 3, we have the mean growth of the thickness of 200 trees in a forest is found to be 0.5 centimeters per year. So there's a total of 200 trees, so that's our n. And then it says the mean growth is found to be 0.5 centimeter per year. So that is my mu, the mean is the average. And then it says standard deviation is 0.1, so that is my sigma. X bar is going to be the same as mu, so it is 0.5. Sigma, or not sigma, S is going to be sigma over n, so 0.1 over the square root of 200. Get my bars in there while you're catching up. Let's get my square root. Hold please. Oh, it's on line already. Line. And then draw my square root. This will be real easy when I move to the, oh, it's a terrible square root. It'll be a lot easier in the next part because we're just going to go to the calculator. Oh no, in a minute. Okay, central limit theorem for means. So here is the formula we already talked about right here. Central limit theorem for means, specifically means. Just so you know, this is the central limit theorem for means because we're going to switch in a minute, and it's these formulas for means. Okay, now we switch. We are going to talk on the second page about the central limit theorem for sums. So this is a little different. Let me just kind of talk about what these two things are doing. So we have a sample. For the central limit theorem for means, we pick some out of our sample and find the average. We pick some more, find the average, pick some more, find the average. And we put all those averages together. We're going to use the central limit theorem for means. Sums says we keep getting larger and larger samples, figure out what the sum is, and then follow the normal distribution. So instead of finding the average of a sample, we're going to say we're talking about test scores. Well, we're going to take this group, add up all their test scores. We're going to take a bigger group, add up all their test scores. Take a bigger group, add up all those test scores. And we're going to put it all together, and it's going to follow this normal distribution. So the central limit theorem for sums is going to be this formula. So x bar is mu times n. It's no longer mu. It's mu times n. And S, our sample standard deviation, or our standard deviation for the central limit theorem for sums, is going to be sigma times the square root of n. And so we have no longer division. That's what I'm trying to say. This is multiplication, not division. Okay, same steps. We are going to do the central limit theorem. Oops, wrong button. Okay, go away. We're going to do the central limit for sum, so we're using these formulas. And so I just did the same problems. Just say we're doing something different this time. We're going to do central limit theorem for sums. So everything is going to be identified the same, meaning this is still n, this is still mu, and this is still sigma. The difference is in the answer. So for the answer for this, x bar is going to be mu times n. You don't even have to multiply it out. You might on the homework, if this is the only thing it's asking for, if it just says find the mean using the central limit theorem for sums, they might give you it, they might say to multiply it out. But for what we're going to do, I don't even need you to multiply it out. And then our S is going to equal sigma times the square root of n. So sigma times the square root of 60. My square root. Again, you don't need to simplify it, just leave it right like that. Okay, so we have our class again of kids with their candy. We have n is 30 kids. The average, or mu, is 73, and the standard deviation, or sigma, is 3. So we're going to find, using the central limit theorem for sums, we're going to find x bar, which is mu times n. And then we're going to find s, which is sigma times the square root of n, 3 times the square root of 30. Okay, you're just going to have to trust with these square roots here. Okay, last but not least, same problem as before. So we know already this is n, this was mu, and this was sigma. Using the central limit theorem for sums, we get that x bar equals mu times n. And this one, a half of 200, you could write 100, that's fine. Whichever way you want to write it. That one, there's no rounding, so that one was real easy. Even 67 times 60 is real easy to put in your calculator. I just can't do it in my head. Okay, and then S equals our sigma times the square root of n, so the square root of 200. I wonder if I could just steal a square root that I liked from the book. Can I copy? Nope. Okay, too much. Draw. Okay, so that's how you find the average and the standard deviation for those two central limit theorem problems. Now we are going to solve. So this is like 6.3 using our new mean, our new way of finding mean, and our new way of finding standard deviation. It's going to kind of be a little weird in the calculator, but we'll get it figured out. So it says, suppose an elevator has a maximum capacity of 16 passengers. So that means n is 16. With a total weight of 2,500, find the probability that a sample of 16 males, okay, we already said that was n, has a mean weight greater than 156.25. What are the chances, I'll write this out in a minute. What are the chances that it's overloaded? Assume a male weights follow normal distribution with a mean of 182.9 and a standard deviation of 40.8 pounds. So we can see down here, we already have our data value. Our x is 156.25. Our mu is 182.9, and our sigma is 40.8. So what we need, because this is a central limit theorem for means problem, let me show you how I know. It says, find the probability. So we always look for where the question is. Find the probability, and then when it's telling us what we're finding the probability of, it has the word mean in it. It doesn't have the word sum in it. So this is a central limit theorem for means problem. The hardest part of this section is going to be knowing when to use means and knowing when to use sums, because you already know the basic formula from chapter 6. These little multiplication problems aren't going to add too much difficulty. It's just going to be a matter of when do you use what. Okay, so we're trying to find the probability that x is greater than 156.25. I know that x bar, because this is the central limit theorems for means, x bar is going to equal mu, so that's 182.9, we have mu written right here. And finally, I know s is equal to 40.8, so sigma, divided by n, which we talked about above, was 16. So I'm going to draw in my fraction lines and then get ready for the calculator. Oops, get that out of here. Give me my square root back. Okay, so now I'm just going to split my screen real quick. Get my calculator right here. And just like before, we're going to go down to distributions. And remember, these follow normal distributions as long as the requirements are met. Our n is small, but it says that they follow a normal distribution, so that's fine. We're good to go. So we go to normal. Now, this is where it gets tricky because I can't, like if I was to invent this calculator, I probably wouldn't use the symbols here. I probably would just use the words mean and standard deviation because they don't want to know what mu is. They want to know what the mean for the central limit theorem for means is, which is x bar. So right here, we're going to type 182.9. That you're going to get right regardless because mu and x bar are the same. This is where it gets tricky because, again, it's asking for the standard deviation, but it says sigma, but we're going to ignore that because we're actually needing this formula for S because the calculator doesn't know that we're doing central limit theorem for sums. So I'm going to go over here on my calculator, and I want to type a fraction. So I have 40.8. Let me do it again. I've divided with the weird time. 40.8 divided by square root is right here above the parentheses, 16. And I go to next, and so that's 10.2. Now it's going to give you a decimal. That's fine. This one actually didn't need to be rounded because the square root of 16 is 4, so it worked out perfectly. But other times this will be like a really long decimal. That's fine. It's not rounding. It's keeping all the information. It's just writing it in decimal form. So that's perfect. I'm going to go to next. And now I have a picture that is greater than 156.25. And notice that almost everything's green. Almost the entire thing's green. You can see over here, it's really hard to see, but hopefully you can see better on yours. There's a tiny little white patch right here, and the rest of it's yellow, almost all of it. And then we can see reflected in the answer, 99.9955. So the probability is almost 100%. So the answer is 0.9955. That is the probability that if that the elevator, the people are going to wait too much for the elevator because we're saying this is if this is their average weight, they're going to they're almost to the maximum capacity of the elevator. Okay, let's try this again. We have the weight. Now there's no more pictures, so we have to draw a picture to see what it looks like. But it says the weight of chocolate bars from a particular chocolate factory has a mean of 8 ounces and a standard deviation of 0.1 ounces. And what is the probability that 15 chocolate bars have a mean weight of more than 8.3 ounces? So I see right here in the question where it says, what is the probability? And then it says a mean weight more than 0.8 ounces. So I know I'm using the central limit theorem for means, and I know this problem is saying the probability that x is greater than 8.03. Okay, so now we got to figure out, that's what we're going to answer. Let's just draw a little picture to see what's going on. So we have our normal distribution. Little pointy, but that's okay. We know that 8 is in the middle, and we're talking about 8.03, so that's bigger than the middle. Let me get my line back. and we're talking about more than. So we are going to color in the more than direction. Just trying to find my colors here. I wish I could just spell this. Okay, this is me shading. Oh, it actually looks like a mountain and someone's like skiing down the mountain. Okay, so from this, we already have mu, we already have n, we already have sigma. So we are just going to write out what we need for the calculator. X bar is the same as mu because we said this is a central limit theorem for means. And get a little number spacing. S is going to equal sigma divided by the square root of n. Now this one has a square root of 15. That's going to be a little uglier on our calculator. So it's not going to have such a nice, neat decimal like we did last time. That's fine. It's all good. All right. So from here, hitting everything. Okay. From here, we're going back. We have to go back to our mean. So our mean is 8. Our standard deviation is 0.1 divided by the square root of 15. See how it's weird now? It's a little tinier. It goes on forever. That's perfect. That's exactly what we want. And now I want the probability. I'm going to change it to greater than. And we have 8.03. And voila, there is our answer. We have 0.1226. Yay! This is going to be repetitive until you can figure out the difference between mean and sum on your own, which will hopefully be on the third assignment of the week. Okay, new problem. I think we just have two more problems. Okay, in a survey of a company, the mean price, it was of a new microwave. Oopsie, why did I write mu next to mean? Okay, let's move this guy over here. Mu, standard deviation, just write sigma off to the side here, was 2120. 100 people were surveyed, and we want the probability that their sum cost was between 29,300 and 29,617. Okay, there's two clues that this is a sum. I'll start with the most obvious clue, and it says find the probability, and then it says sum cost. So it says the word sum right there, right? Sum. The second most obvious clue is these numbers are ridiculously huge compared to average. Remember, for this section, for central limit theorem for sums, we are multiplying mu times n. So that's going to give really big numbers. In this example, n is 100. So it's going to give really big numbers. So it makes sense that we're doing this between part. The between is really big numbers as well. So for starters, we have the question, which is what is the probability? And we're going between 29,300 and 29,617. That's what we're asking. Let's draw a quick picture. We have our normal distribution. Lovely. The middle, well, let's just come over here. Well, let's just do two things at once. I'll finish up the picture in a minute. But X bar is going to be mu times n. And so I'm just trying to get a semi-accurate picture here just so we can kind of match this. 293.21 times 100 is 29,321. So that means the first number is a little bit less than the middle. And the second number, 29,321, is a little bit, is kind of more than the middle. So it's going to be somewhere like that with our coloring in between because it says the cost is between. Okay, and now we have finally our sigma, no, our S, which is going to be sigma times the square root of n, not divided by. This time we're doing times because it's the central limit theorem for sums. Try to get my draw. It's hard when it's like in the middle. There we go. It's going to be a weird square root, but it's okay. That's what the square root is. Okay, back to our calculator. Mu is now 293.21 times 100. When I hit enter, it multiplied it for me. Perfect. I don't know what's going on. I don't know why that number's so small. Okay, whatever. 21.20 times the square root of 100. All right, it worked out to a nice whole number because the square root of 100 is 10. Perfect. It doesn't matter if it's a decimal, a whole number, whatever. But remember, the important thing to remember is this is not mu from the problem. This is x bar from the problem. This is s from the problem. And last but not least, I want to go in between what two numbers? It tells me 29,300 and 29,617. Hit enter. Kind of looks like my picture here. And it says, well, let me go over. Oh, hang on a second. 29,617. There we go. You can see the whole number. So I know rounded to 4 decimal places is going to be 0.4581. Okay. Last one for today. Question 1. Central limit theorem for seams, central limit theorem for means, or central limit theorem for sums. So when the question says what is the probability, it's telling us we're looking for the sum is less than 13,215 pages. So it says the word sum, but also 13,215 is like a ridiculously large number, so that's another clue that it sums. But the best clue is that it says the word sum. Okay, so I have in my problem the average length, so average is mu, tells us this is the standard deviation, so there's sigma, and can't really fit it in, but n, I'll just draw an arrow to it. N is right there. Okay, next up, probability. Notice when we're writing out the, right here, we're not worrying about the sum. We're just using that when we go to the calculator. The probability of the sum is less than 13.215. Okay, so we have, oh, it's an arrow, that's why I got messed up. Okay, here's our picture. Lovely. I don't know what our average is. Our average seems quite large. 350, oh no, times 37, never mind. I don't know what that is in my head, so I'm not really sure if this is going to be greater than a half or less than a half, so I'll just draw a line. But I do know that it's less than, so I know we are shading over here. Shade, shade, shade. Okay, so now for this last problem, we have x bar equals mu times n and sigma, no, s equals sigma times, not divided by, times the square root of n. So I'll just get my square root going, and then we will put it in the calculator. Ooh, it's going to be official square root. Okay, I don't like that. It's going to mess up. Square root over the 37. All right. Back up. Mean is 350 times 37. S is, or standard deviation is 100 times the square root of 37. Oh, go back. See how it's a decimal? Who cares? It's all good. Down. Okay. Last but not least, it's already at less than. So I need to put in 13,215. There we go. And our final answer is for the probability that the sum of the pages is less than 13,215 pages, we get 0.6685 when rounding to 4 decimal places. Okay, I just lost my face. Oh, there I am. So the moral of the story is this is what we're doing this week. That was kind of fast, kind of me doing everything. As we move on through the week, then I'm going to give some more pauses in the video to give you a chance to catch up. And probably by the last video, there isn't going to be a video because you're going to be so good at it. But we'll just do like one of those quick check answer videos. If you have any questions, send me an email and I will see you in the next video. Bye.